Hello, everyone. My name is Rafid Badi Murad. I am a PhD candidate at Cornell University, and today I'm going to talk about predicting the suitability of ionic liquids for electrospray propulsion using machine learning. This is the outline of the presentation. I will start by giving a brief motivation for this work. Then I will present the approach, the database, and the different algorithms that we use. And then I will show the results and the evaluation of the algorithms and the newly discovered candidate propellants. Then I will discuss some future perspectives, and then I will conclude. So electrospray thrusters apply a strong electric field to extract ions from ionic liquid. These ions exit the thruster at about 50 kilometers per second, and due to the conservation of the momentum, this creates some thrust that will push the spacecraft forward. And the physical properties of the ionic liquids influence the performance of the thruster and its lifetime. The ionic liquid is composed of a pair of a cation and an anion. And there are thousands of cations and anions in nature, so potentially we can synthesize millions of ionic liquids. However, despite this huge number of possible ionic liquids, only a small number is used for electrospray thrusters. And mainly EMI plus BF4 minus is the most used ionic liquid for electrospray thrusters. But we can safely assume that among these millions of ionic liquids, there exist some ionic liquids that can be used for electrospray thrusters, and these need to be discovered. However, a comprehensive experimental characterization is not feasible, so we need a computational model to exploit the sparse available experimental data and evaluate unknown ionic liquids. And it has been shown from electrohydrodynamic simulations and experiments that for an ionic liquid to be considered as a good candidate for electrospray thrusters, it has to satisfy some physical properties in terms of surface tension, viscosity, density, electrical conductivity, electrochemical window, and solvation energy. However, due to the unavailability of data, in this study, we're only going to focus on the first three requirements. So for the next of this presentation, if an ionic liquid satisfies these three requirements in terms of surface tension, viscosity, and density, it will be considered as a good candidate for electrospray thrusters. And this is the general goal of this study. So we have a database of ionic liquids. So we have the cations and the anions, along with the density, viscosity, and surface tension. Then we apply filters based on these properties, and we label the ionic liquids as +1, which means suitable for electrospray thrusters, or -1, which means unsuitable for electrospray thrusters. And then through a learning process using machine learning, we want to learn some molecular structures in these ionic liquids to build a classifier. And this classifier will be able to predict the suitability of ionic liquids without knowing their physical properties. So this classifier will be used for ionic liquids with unknown properties to predict if they are suitable or not for electrospray thrusters. Now I will talk about the approach that we follow. So I will start by talking about the database and the representation of the molecules in this database. So the molecules are represented using the SMILES representation, that stands for Simplified Molecular Input Line Entry System, which is a notation that allows to represent a chemical structure in a string of characters. And it is designed to be both human readable and machine passable. We have here, for example, some symbols that are used in SMILES. For example, C and O represent carbon and oxygen atoms. The parentheses represent the branches. The dash represents the single bond. The equal sign represents double bond. The dash sign represents the triple bond. The column represents the aromatic bond, etc. And you have many other SMILES representations. And here on the right, we have the representation of the cation EMI plus and the anion BF4 minus in this SMARS notation, as we can see here. And then from the SMARS representation, we can use the RDKit library in Python to represent the molecule in a molecular graph. In the molecular graph, the atoms are represented by the nodes of the graph, and the bonds are represented by the edges of the graph. And then we use the Mordrad library to represent the molecules in an array of molecular descriptors. So the Mordrad library can calculate more than 1,800 molecular descriptors, and these descriptors can describe the molecule and its constitutional, topological, geometric, and electronic properties. And it is widely used in drug discovery and material science. And there are 1,800 descriptors. So here we have a few examples. For example, there is the topological radius, which is the graph theoretical radius. That is the number of atoms between the central atom in the graph and the farthest atom in the graph. There is the geometric radius, which is the actual physical radius. There is the molecular weight. There is the number of aromatic rings. There is this log P that represents the hydrophobicity of the compound, etc. So we start with a summarize representation that is a representation of the molecule in a string of characters. Then we go to a molecular graph representation. Then we go to an array of numbers, and each array represents the molecules, and each element of this array represents a given descriptor of the molecule. And we have three databases. All of them are from Paduzinski. And these represents the density, viscosity, and surface tension. And the dashed red line represents the threshold that we want our ionic liquid to satisfy. And we have in these three databases, we have 2,261 ionic liquids. However, most of them are rejected. So among all these ionic liquids, there is 1,782 that are rejected because they do not satisfy at least one requirement. And we have only 14 accepted ones because they satisfy all the requirements. And there is 465 uncertain examples because there is missing data. So we cannot tell if they are accepted or not. And we present them in this figure here. So we have the anion mass versus the cation mass. And we have the rejected molecules in red, the uncertain ones in blue, and the accepted ones in green. And EMIBR4, which is the most used ionic liquid for electrospray thrusters, is represented in this square here. However, as we can see here, the data is extremely imbalanced. So we have only 0.8% of positive examples. And if we keep the data as it is, the classifier is going to be biased towards the majority class. So we need to use some techniques to treat these imbalanced data. And for this, we use some resampling techniques. So it is recommended to use oversampling of the minority class, followed by the undersampling of the majority class. For oversampling, we use this algorithm called SMOTE, that stands for Synthetic Minority Oversampling Technique. For example, if you want to classify blue circles from red squares, and the red squares are a minority compared to the blue circles, then we can look for the nearest neighbors of these red squares and then create some synthetic data to balance the data set. So we have an equal number of circles and squares. And there are different parameters that we can tune for oversampling. And we can also do undersampling, so we ignore some points from the majority class. And also there are also different parameters in undersampling, and we can also tune the number of nearest neighbors used for the SMOTE algorithm. Now I will talk a little bit about the four different algorithms that we use for classification. There is logistic regression, support vector machine, random forest, and XGBoost. So in the logistic regression, we try to estimate the probability that a given instance belongs to a positive class using a logistic function. And if this probability is higher than a threshold, say 0.5, then we predict +1. Otherwise, we predict -1. And in order to avoid overfitting and make the model more generalizable, we do some regularization. And there are different parameters for regularization that we can tune as well, as we can see here in this table. The second algorithm is support vector machine, SVM. The SVM tries to maximize the margin. The margin is the minimum distance between the classifier and the data points. And here also we use regularization to avoid overfitting. And we use as well kernels. So if the data is not linearly separable in a small dimension, small d, the kernels can represent the data in a higher dimension, big D, that is much larger than small d. And in this higher dimension, the data is linearly separable. So we use kernels for the SVM to make the model stronger. And there are also different parameters that can be tuned. And we do the tuning during the grid search, as we will see later. And the third algorithm is the random forest. The random forest is an ensemble technique or learning method that combines multiple decision trees. And each tree makes a prediction. And the random forest uses a majority voting from all the trees to make the final prediction. And there are different hyperparameters that we can tune here as well. For example, we can tune the number of trees, the maximum tree depth, the minimum samples for splitting, etc. Finally, there is the extreme gradient boosting called XGBoost. So this one is a series of decision trees that are called weak learners. Each weak learner makes many mistakes, and in the next step, the weight of the mistakes is increased. So the second weak learner can learn from the mistakes of the first one, etc. So until the last one, the last classifier can learn from the mistakes of all the weak learners. And also here, there are different hyperparameters that can be tuned. For example, we can tune the number of weak learners and the learning rate, etc. Now we will talk about the performance metrics that are used to evaluate the algorithms. So there is precision, that is the ratio of true positives over true positives plus false positives. So precision tries to maximize the true positives while minimizing false positives. There is the recall that tries to maximize true positives while minimizing false negatives. And there is the F1 score, that is the harmonic mean of precision and the recall. So this is a balance between the two. And for our study, we choose the F1 score as the metric to be used for evaluating the algorithms. So this is the general workflow of this work. So we have a summarized representation of the ionic liquids with their physical properties. We apply some filters and we make the actual labels. Then we calculate the molecular descriptors and represent the molecules in an array of numbers. And then we apply some resampling techniques. So we do some oversampling, undersampling, scaling. We apply this to all the classifiers and we do a 5-fold cross-validation. And then we predict the labels and then we compare the actual labels with the predicted labels and then we compute the precision recall and the F1 score. Now when we talk about the results of the different algorithms, so in these tables we have the confusion matrix, the precision, the recall, and the F1 score for training and testing for the different algorithms. And after examining all these numbers, we find out that the SVM is the best performing algorithm with the highest F1 score and the highest precision. So we will use the SVM for the rest of this study. Now we'll talk about the newly discovered candidate propellants from the dataset of ionic liquids. So as I mentioned earlier, we have only 14 positive examples, and we have 465 uncertain examples. So now we will apply the classifier to these uncertain examples, and the results show that we have 19 new positive examples. So we have 19 new candidates that can be used for electrospray thrusters. However, since the precision is 60% only, so we expect to have 11 true positives and 8 false positives. And here are some examples of the newly discovered candidate propellants. So we have the cations here and the anions here. So we have all the different pairs. And these are just 8 among the 19 that have been discovered. And the second step here is that we are not completely satisfied with only 19 candidates, so we want more candidates. So we take all the unique cations that we have in the dataset, and we pair them with the unique anions that we have, and we get about 250,000 ionic-like molecules. So we call them ionic-like molecules because there is no guarantee that these combinations are actual ionic liquids. And then we calculate the molecular descriptors of all these 250,000 ionic liquid-like molecules, and then we apply the SVM classifier, and then we will show the results. So among the 250,000 ionic liquid-like molecules, there is 193 positive examples. Among these, there is 14 that are positives from direct filtering, and they are represented with green circles. There's 19 that are accepted from the actual data set, and they are presented in this black crosses. And there's 160 that are accepted from the constructed data set, and they are represented with the blue diamonds. And on the left here, we have the full space of the mass of the anion and the cations. And as we can see, the positive examples are located in this restricted space. And this is because the training space at the beginning was also restricted. So the classifier can only learn from this space here and do some interpolation. So it cannot go very far from the learning space. So in actuality, we can have some positive examples in this outside region. However, the classifier was not able to reach it. So that is why all the positive examples are located in this region. Now we'll talk about some future work. So in this study, we used the data set and we labeled it, and we used some classifiers uh, to predict if a given ionic liquid is accepted or rejected. So for the future, we want to take the accepted ones and characterize them using molecular dynamic simulations or experiments. And if they are still accepted at this step, then they can be used for electrospray thrusters. Otherwise, if they are rejected, that they can be used to refine the labels of the dataset. And we can do this iteratively. So for a conclusion, so in this study, we have calculated the molecular descriptors of ionic liquids from their smart representation. We have labeled the data based on density, viscosity, and surface tension. We have applied the resampling techniques to address imbalanced data. And we have tested 4 different algorithms: the logistic regression, the SVM, the random forest, the XGBoost. And the SVM showed the best performance. And we have identified 193 potential propellants for electrospray thrusters, which is the main result. And for the future, we want to validate our ML predictions with MD simulations and experiments. And also, this framework that we constructed can be generalized for other applications requiring molecules with specific properties. So this work is not restricted for ionic liquids only or electrosprays only. So it can be used for other applications in engineering or industry. But this, and thank you. I hope it was useful.